I'm Anil Kumar. Welcome to my website, Global Math Institute. In this video, we'll discuss proof by mathematical induction. Here are 8 examples. They are very similar questions in every statement. You can see that we are interested in proving that something is divisible by something else. And we'll discuss different strategies and methods to solve such questions. Here are 8 problems to practice. You can pause the video, copy these questions, and then look into my suggestions. Let's begin with the very first one, which is right here. So we'll prove that 9 to the power of n minus 2 to the power of n is divisible by 7 for all n belonging to natural numbers. So we have 9 to the power of n minus 2 to the power of n. Do you see 9 minus 2 is 7? So that gives you the idea that it will be divisible by 7. So we have to prove that this is divisible by 7. Let's call this as our function f of n, right? So let's say f of n is equal to 9 to the power of n minus 2 to the power of n. We'll understand this method of mathematical induction also, in which we first check for the first value. If n equals to 1, then is the statement true or not? Substituting 1, we get 9 to the power of 1 minus 2 to the power of 1, which is 9 minus 2, which is 7. And so we say that f of 1 is divisible by 7. Right? So that is the first step. Now we assume and we say let f of k be divisible by 7 also. So we'll just substitute k for n, and we'll assume that 9 to the power of k minus 2 to the power of k is equal to a multiple of 7. So we can write this as 7 times lambda. Here we have assumed f of k is a multiple that is divisible by 7, right? Is a multiple of 7. Clear? Okay. So if it is a multiple, you can write this as 7 times something. We're using lambda, right? 7 times lambda. What we need to really prove now is that f of k plus 1 should be divisible by 7, right? So we'll figure out what is f of k plus 1. So f of k plus 1 will be 9 to the power of k plus 1 minus 2 to the power of k plus 1. Now, that could be written as 9 times 9 to the power of k minus 2 times 2 to the power of k. Now, we can write 9 as combination of 7 and 2, right? So I could write this 9 by switching this to 7 plus 2. And we get here 9 to the power of k minus 2 times 2 to the power of k, correct? So we'll just do readjustments, that is 7 times 9 to the power of k minus, let's write this, plus 2 times 9 to the power of k minus 2 times 2 to the power of k, right? So 2 is common between these two. So we can write this as 7 times 9 to the power of k plus 2 is common. So we get 2 times 9 to the power of k minus 2 to the power of k. Now we had already assumed that 9 to the power of k minus 2 to the power of k is 7 times lambda, right? So we'll call this as our equation number 1. So we can replace 9 to the power of k minus 2 to the power of k with 7 lambda. And therefore, we can write this as equal to 7 times 9 to the power of k plus 2 times this portion here is 7 times lambda. Right? Now, 7 is common between these two, so we can write 7, and within brackets we get 9 to the power of k plus 2 times lambda. So clearly it is a multiple of 7, right? And therefore we can write that since f of k plus 1 is divisible by 7, f of n is also divisible by 7. Is that clear to you? So with the method of induction, we can, like this, show that the given expression or the function is divisible by the given number. So now let's take a general case where we have proved that x to the power of n minus y to the power of n is divisible by x minus n for all n belonging to natural numbers. So again, we'll begin by f n as equal to x to the power of n minus y to the power of n. So we'll check for n equals to 1. So we get x to the power of 1, y to the power of 1, and that is definitely divisible by x minus 1, right? So we see that f of 1 is multiple of x minus y. Clear? Now we'll assume f of k, any general term, to be a multiple of x minus y. So we'll write this as x to the power of k minus y to the power of k, and we'll assume this to be equal to lambda times x minus y. Correct? So that is the assumption. Now the idea is that we need to prove that f of k plus 1 is divisible by x minus y, right? So let's find what is f of k plus 1. So f of k plus 1 will be x to the power of k plus 1 minus y to the power of k plus 1. Now that can be written as x to the power of k times x minus y to the power of k times y. Now to prove this, we are adopting a different strategy this time. We are adding and subtracting a term which will involve x to the power of k and y. So we'll subtract x to the power of k times y, and we'll also add x to the power of k times y. So that makes really no difference. Now, if I combine these two terms and these two terms, then what do I get? So let me rearrange and write. So we get x to the power of k times x minus x to the power of k times y. And here we have plus x to the power of k times y minus y to the power of k times y. Now in the first two terms, x to the power of k is common, and what we get is x minus y. Now here we can take y common, right? So we can take y common, and what we get here is x to the power of k minus y to the power of k. Now this statement here, which is our assumption, is that f of k is true. Now that is that x to the power of k minus y to the power of k is lambda times x minus y. So we can substitute that here. So what we get here is x to the power of k times x minus y plus y times lambda times x minus y. So x minus y becomes a common factor. And what we get here is x to the power of k plus y times lambda or lambda y. Clearly, from here we know that f of k plus 1 is divisible by x minus y. And therefore, we can conclude that x to the power of n minus y to the power of n is also divisible by x minus y. Is that clear to you? So that is how we can prove it. Perfect. Now, let's take the third example, which is a variation of this. So this time what we have for you is x to the power of 2n minus y to the power of 2n is divisible by x plus y for all n belongs to natural numbers. I'd like you to pause the video, answer this, and then look into my suggestions. So I hope you got the solution. Question number 3 here is to prove that x to the power of 2n minus y to the power of 2n is divisible by x plus y for all n belongs to natural numbers. So we'll again begin with writing this as a function of n, which is equal to x to the power of 2n minus y to the power of 2n. For f of 1, let's check if it is really divisible by x plus y. So we get x squared minus y squared, which can be written as x plus y times x minus y. So definitely this is divisible by x plus y, right? So that is true. So f of 1 is divisible by x plus y, right? So this statement is true. Now we are going to assume that f of k is equal to lambda times x plus y. So this is what we are going to assume. So let's figure this out. So we have f of k as equal to x to the power of 2k minus y to the power of 2k. Correct? Now what we need to prove is whether f of k plus 1 is divisible or not. So we get x to the power of 2 times k plus 1 minus y to the power of 2 times k plus 1. Correct? That is what we need to prove. So what is this equal to? We can write this as x to the power of 2k times x squared minus y to the power of 2k times y squared. Now, as we did in the last example, we'll again add and subtract a term so that we could show that there is a common factor. So looking into this, the term which we are going to add is x to the power of 2k and y squared. Does it make sense to you? Right? So we'll pick up a factor from here and another factor from this place, right? So what we'll do here is we'll rewrite this as x to the power of 2k times x squared. And we are going to add a term here since we want x plus y. So we'll write here plus x to the power of 2k y squared and minus x to the power of 2k y squared. Do you see the strategy? Right? And we already have the second term, which now becomes the fourth term as minus y to the power of 2k times y squared. Perfect. Now from here, we can take common factors and then show that the given function is indeed divisible by x plus y. So we'll write this as f of k plus 1 as equal to. Now here, x to the power of 2k is common, right? We get x to the power of 2k and we get x squared plus y squared. And in this case, we get, in fact, what we should do is we'll take the first and the third term. We'll take these two terms, right? Since we want minus, right? Do you see the sign minus? So we like to maintain that. So we'll take first and the third term, and then we'll take the second and the fourth term. Is that clear to you? And so we get, taking second and the fourth term, y squared is common. So we get plus y squared. And what we get here is x to the power of 2k minus y to the power of 2k. So we have a common term which is x to the power of 2k minus y to the power of 2k. And within this bracket, we get x to the power of 2k plus y squared. Perfect. Now, x to the power of 2k minus y to the power of 2k has been assumed to be equal to lambda times x plus y, right? So that is our assumption. So we are going to substitute this here. So we can write this as lambda times x plus y, and here we have x to the power of 2k plus y squared. So clearly we have shown that f of k plus 1 is divisible by x plus y. Therefore, x to the power of 2n minus y to the power of 2n is also divisible by x plus y using method of induction. Is that clear? So let's continue. Question number 4. Prove that 9 to the power of n minus 2 to the power of n is divided by 7 for all n belongings to natural numbers. Well, we actually copied our question number 1 here, but I'll prove this with an alternate method, right? So we'll use the alternate method here. So we'll again define our function as f of n as equals to 9 to the power of n minus 2 to the power of n. When we use the method of induction, we can write f of 1 as equal to 9 to the power of 1 minus 2 to the power of 1, which is definitely 7. So it is true that f of 1 is divisible by 7. Now we are going to assume that f of k is also divisible by 7. So which is 9 to the power of k minus 2 to the power of k is equals to some lambda, a parameter, times 7. So it is divisible by 7, right? So that is divisible by 7, right? So that is the assumption. So now we need to prove that f of k plus 1 is divisible by 7, right? So what we have to do now is to prove that f of k plus 1, which is 9 to the power of k plus 1 minus 2 to the power of k plus 1 is divisible by 7, right? So that is what we need to prove. So this is equal to 9 times 9 to the power of k minus 2 times 2 to the power of k. To prove this, what we can do is that we can add and subtract a term just as we did in our question number 2, right? Solution. So 9 times 9 to the power of k. Since we need minus here, so we'll subtract a term which will have 9 to the power of k times 2, and we'll also add 9 to the power of k times 2. And we have 2 times 2 to the power of k. Now combining the first two terms where we have 9 to the power of k common, we get 9 minus 2. And in the next two terms, we have 2 common, right? So we have plus 2. And we can write this as 9 to the power of k minus 2 to the power of k. 9 minus 2 is 7, so we can write this as 7 times 9 to the power of k. And here we have 2 times lambda 7, right? So this portion is 7 lambda, since that is our assumption. So from both these equations, we can take 7 as a common factor, and what we get is 9 to the power of k plus twice lambda. So that clearly shows that f of k plus 1 is divisible by 7, right? So we can write, since f of k plus 1 is divisible by 7, 9 to the power of n minus 2 to the power of n is also divisible by 7. Is that clear? So that becomes the proof, correct? Now what you could do here is, you could actually change the question if you want. So let's say we'll do question number 4b, and instead of 9 to the power of n, you can write this as 7 to the power of n minus 2 to the power of n is divisible by 5, correct? So you can follow this method. So this is a standard method. So you could adopt the method which we used in solution of the first one, or this one, right? So here is our previous method which we applied. Perfect. So you could use either of these methods to solve such questions. I hope that makes sense, correct? Now let's take question number 5. Question number 5 is to prove that 2 to the power of n plus 2 plus 3 to the power of 2n plus 1 is divisible by 7 for all values of n. So again, we'll define our function f of n as equal to 2 to the power of n plus 2 plus 3 to the power of 2n plus 1. So what is f of 1 equal to? F of 1 will be 2 to the power of 3 plus 3 to the power of 2 plus 1, which is 3. Now this is equal to 8 plus 27, right? So which is 35. And so if we find that it is true that f of 1 is divisible, 35 is divisible by 7, right? Now what we are going to do here is, we are going to assume that f of k is equal to 7 times lambda. It's also divisible, right? That's what we are going to assume. So we can write 7 times lambda as equal to 2 to the power of k plus 2 plus 3 to the power of 2k plus 1, right? So we'll call this as our equation number 1. What we need to prove is that f of k plus 1 is divisible, right? So we need to find what is f of k plus 1. So that will be 2 to the power of k plus 1 plus 2 plus 3 to the power of 2 times k plus 1 plus 1, right? So you could write this in brackets. Take this to the right hand side and solve further. So we have f of k plus 1 can be written as. So we can open this. Since we are given 2 to the power of k plus 2 plus 3 to the power of 2k plus 1 as 7 lambda. We'll try to get that figure now, right? So we could rearrange and write this as 2 to the power of k plus 2 times, so that is k plus 2, and we have 2 to the power of 1, which is 2 left, right? Plus, here we get 3 to the power of 2k plus 1, this one, right? 2k plus 1 times, here we get 3 square. Okay. So now, 3 square is 9, so we can write this as 2 times 2 to the power of k plus 2 plus 3 square is 9, so 9 times 3 to the power of 2k plus 1. 9 can be written as a combination of 7 and 2. So we can write this as 2 times 2 to the power of k plus 2 plus 2 plus 7 times 3 to the power of 2k plus 1, which is 2 times 2 to the power of k plus 2 plus 2 times 3 to the power of 2k plus 1 plus 7 times 3 to the power of 2k plus 1. Now here 2 is common, so we can write 2 common, and we get 2 to the power of k plus 2 plus 3 to the power of 2k plus 1, and that gives you 7 times 3 to the power of 2k plus 1. Now this first portion is given to us as 7 lambda. That is our assumption, right? This is a multiple of 7. So we can write this as 2 times 7 lambda plus 7 times 3 to the power of 2k plus 1. So now 7 is a common factor, right? So 7 is a common factor. So let me write 7 common. We get 2 lambda plus 3 to the power of 2k plus 1. Clear? So clearly, we have shown that f of k plus 1 has 7 as a factor, right? Therefore, we have shown that f of k plus 1 is a multiple of 7, correct? So that is how by induction, so we can say by induction, so by principle of induction, f of n is divisible by 7. Is that clear to you, right? So that is how we can prove it. So I hope the steps are absolutely clear. Let's take the next question, which is question number 6. Now we need to show that 2 to the power of 3n minus 1 is divisible by 7, right? So we have learned many strategies. I'd like you to pause the video and adopt one of those to prove. So we'll define the function f of n as equal to 2 to the power of 3n minus 1. To prove by the method of induction, we'll check first for n equals to 1. So we have 2 to the power of 3 minus 1, which is 7. So definitely this is true, right? It is divisible by 7. So we'll assume that f of k is also divisible, so it is lambda times 7. So we'll write 7 lambda as equal to, writing k here, we get 2 to the power of 3k minus 1, correct? And we'll call this as our equation number 1. What we need to do now is to prove that f of k plus 1 is also divisible by 7, right? So if I replace n by k plus 1, we get 2 to the power of 3 times k plus 1 minus 1. Clear? Let's take it to the right side to rearrange and then prove it. What I will do in this particular case, I'll kind of, you see, we have 2 to the power of 3k minus 1 as 7 lambda. So equation 1 can be rearranged and we can actually write 2 to the power of 3k as also equal to 7 lambda plus 1. So I'm changing my strategy a bit. I'm going to use this equation number 2 to this time prove by induction. So what we have here is f of k plus 1 is equals to 2 to the power of 3 times k plus 1 minus 1, right? So let's expand this. So we get 2 to the power of 3k plus 3 minus 1. Now, so which is equals to 2 to the power of, we have 3k times 2 to the power of 8 minus 1. Now 2 to the power of 3k we have written as 7 lambda plus 1. So we'll write this as 7 lambda plus 1 times 2 to the power of 3, which is 8 minus 1. Correct? So let's open the bracket. So we get, which is 8, right? So we get 8 times, let me write once again, 7 lambda plus 1 times 8 minus 1. So that gives us 56, which is multiple of 7 lambda plus 8 minus 1, or 56 lambda plus 7, correct? You could also write this as, well, you can take 7 common, 8 lambda plus 1. So clearly what we have shown here once again is that 2 to the power of 3n minus 1 is divisible by 7, since f of k plus 1 is divisible by 7. Is that clear to you? So this is another strategy. You can actually at this stage rearrange and then substitute as we did here, and that helps. I hope these strategies help you to prove these divisibilities by the method of induction. Now at this stage, I'd like you to try the next 2 questions yourself, which is our question number 7. You need to prove that 10 to the power of 2n minus 1 plus 1 is divisible by 11. And then question number 8. So try these. We'll be back with you after a short break. We'll now work on question number 7, which is to prove that 10 to the power of 2n minus 1 plus 1 is divisible by 11 for all n belonging to natural numbers. So in the method of induction, as you learned, we have to first show that for n equals to 1, this is true, right? So we'll define our function f of n as equal to 10 to the power of 2n minus 1 plus 1, and we'll test what is f of 1 equals to. F of 1 is 10 to the power of 2 minus 1, which is 10, right? So let me write 1 here, plus 1, and that is indeed 11. So we know that f of 1 is divisible by 11. Now what we need to do is we need to assume that f of k is also divisible by 11. So f of k is equals to 11 times lambda. So we can write 11 times lambda as equal to, we'll replace n with k, so we get 10 to the power of 2k minus 1 plus 1. Well, I have 2 different strategies to work with. Sometimes what you could do here is that you could rearrange and write 10 to the power of 2k minus 1 as equal to 11 lambda minus 1. So you could use either one of these equations. So at times you could use equation number 1, or you could also use this equation to prove that f of k plus 1 is also divisible by 11, right? So now the idea is to find what is f of k plus 1. So f of k plus 1 will be 10 to the power of 2 times k plus 1 minus 1 plus 1, correct? So let's take it to the right side and simplify. So f of k plus 1 is indeed equals to 10 to the power of 2k plus 2. So we can write this as 2k minus 1 plus 2, right? I'm just rearranging. So which you could write here as 10 to the power of 2k minus 1 times 10 to the power of 2 plus 1, right? Now, we rearranged and wrote 10 to the power of 2k minus 1 as 11 lambda minus 1. So I could write this as 11 lambda minus 1 times 10 square, which is 100, plus 1. So that is 100, right? So we can now open this bracket. So once you open this bracket, what do you get? You get 11 lambda times 10 square minus 10 square plus 1. Now 10 square is 100, so 101 is 99. So what we get here is 11 lambda times, let's write this as 100, minus, that is 99, right? 100 plus minus 100 plus 1. And from here 11 is a common factor. So taking 11 as a common factor, we get 100 lambda minus 9. So clearly f of k plus 1 is a multiple of 11. So from here we can write down that f of k plus 1 is divisible by 11, and therefore 10 to the power of 2n minus 1 plus 1 is also divisible by 11. This is using the first principle of induction, right? So this is application of first principle of induction. Now let's move on and take the last question, which is question number 8 for us. You need to now prove that 2 to the power of 6n plus 3 to the power of 2n minus 2 is divisible by 5 for all values of n. You can always pause the video, answer this question, and then look into my suggestions. So we'll define our function f of n as equal to 2 to the power of 6n plus 3 to the power of 2n minus 2. So for f of 1, what do we get? So we get 2 to the power of 6 plus 3 to the power of 0, right? So which is 2 to the power of 6 is 64 plus 1, which is 65. So clearly it is divisible by 5. So we have f of 1 is divisible by 5, right? So that part is true. So now we are going to do an assumption, and our assumption is that f of k is 5 lambda, is also divisible by 2, right? So that is our assumption. F of k is a multiple of 5. And what we need to prove is, so basically we are saying that 5 lambda is equal to, if I write k here, we get 2 to the power of 6k plus 3 to the power of 2k minus 2, right? So that is our equation number 1. So we have different kinds of proofs. You could also rearrange this equation and write in different fashion, right? So we'll leave it here. And the idea here is now to find whether f of k plus 1 is a multiple of 5 or not. So k plus 1 will be 2 to the power of 6 k plus 1 plus 3 to the power of 2 k plus 1 minus 2. Right? So let's take it to the right side and then solve this. So we get f of k plus 1 as equals to, since we have this form, we'll write this as 2 to the power of 6k times 2 to the power of 6, right? And the second term will be 3 to the power of, we should write this as 2k minus 2, right? So we get 2k minus 2 times 3 to the power of 2, right? Which is 9. So that is how we can write this. And this 2 to the power of 6 is 64. So we get 64 times 2 to the power of 6k plus, and that is 9, right? 9 into 3 to the power of 2k minus 2. Now 64 can be written as 55 plus 9 times 2 to the power of 6k plus 9 times 3 to the power of 2k minus 2. And now from here, we can write one term as 55, which is a multiple of 5, times 2 to the power of 6k plus 9 times 2 to the power of 6k plus 9 times 3 to the power of 2k minus 2. So what we get here is 55 times 2 to the power of 6k plus 9 common. So we get 2 to the power of 6k plus 3 to the power of 2k minus 2. Now this term here is 5 lambda. So we can write this as 55 times 2 to the power of 6k plus 9 times 5 lambda. So 5 is a common factor, and what we get here is 11 times 2 to the power of 6k plus 9 lambda. Is that clear? So clearly we have shown that f of k plus 1 is divisible by 5, right? So therefore f of k plus 1 is divisible by 5. Perfect. And that implies that the given function 2 to the power of 6n plus 3 to the power of 2n minus 2 is divisible by 5. So I hope that makes sense. So with this, we come to an end of our set of videos on practicing with the method of induction to prove. So these are the 8 questions which we tried successfully. Here you will notice that question number 4 was kind of repeated, right? But we used 2 different methods to do this question, right? So we had alternate method here. So to prove such questions by the method of induction, as you have seen here, many alternate methods can be adopted. So try to practice using different methods to solve these questions. I hope that helps. Feel free to write a comment, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.